All right, so what I want to do is I want to pick up with the stuff we started talking about with second order circuits the other day. All right, so before I even do this quick review, so second order circuits means what? What's different about a second order circuit than a first order circuit?
You have multiple
Energy storage devices.
Yep, multiple storage devices. Yep. All right, so it basically means multiple inductors, inductor capacitor, that kind of stuff. Now, one of the things that we said, maybe the most critical thing, is that when I have multiple storage devices, if I just had a first order circuit, right? With a first order circuit, the responses are, you know, shall I say, they're boring, right? So currents and voltages do this. They basically start at some value and end at zero, or they start at zero and go somewhere else, right? And they always get constant by the time we're done. Now, what's different about a second order system? Do the currents and voltages necessarily do they always get constant necessarily?
It oscillates.
Yeah, they can have these sort of bizarre behaviors because energy can be exchanged back and forth. And so we did the example where I compared it with a pendulum, right? So I just basically said, okay, since you were, I don't know, 2 years old and the first time you got on a swing, right? A swing is basically a pendulum where you start out with all potential energy and you get to all kinetic energy, and then you get to all potential energy again, and you basically go back and forth in this process. And you know, ideally, you would get a sinusoidal response from just a second order system, okay? Making a very general statement about a quote unquote second order system. All right, and you know, what we said is that these things are pretty common. All right. And so, and I gave this, you know, sort of example of where these guys sort of occur, you know, and I talked about this thing here, which was a PV inverter. So what could be over here is, you know, this would be where I have some sort of a solar panel or solar array. All right. So I usually draw a PV panel like that. This guy is DC, and then I hook up to the AC grid. So the power grid, which is going to have sinusoidal voltages on the other side. Now, what reason I bring this up is I said last time the voltages across these switches. So these things over here, these blue guys right here, these things are called transistors. Okay. And I said very briefly, and probably nobody remembers it, but let's see if they do. What is a transistor? I said it very
dependent source.
You said it's a switch.
It's a switch. Yeah, and I can model them as dependent sources in some cases, but they're basically a switch. So we talk all the time, you have all these goofy circuits that have switches in them, right? You know, well, at t equals 0, we move the switch. Well, that doesn't mean that we're playing with like Frankenstein switches, you know, and things like that, or light switches, right? The switches we deal with oftentimes are what we call solid state, or they're transistors. And they're incredibly useful, right? Your phone right now has probably somewhere in the order of about 4 or 5 billion transistors, all right, inside of it. All right, they're just switches moving on and off. And the voltages across switches, depending on certain things, can have this kind of behavior like this. When I see behaviors like that, I know that I have a second order system. All right. Now, I point this out basically to say that, well, yeah, second order circuits are pretty common, right? So this is a pretty common circuit, you know, of an inverter that goes from DC to AC like this. And switches are pretty common. Transistors, of which we have many in our digital devices, are very common. All right, so understanding how to deal with switches and this sort of dynamic transient behaviors is really important, okay? All right, so to continue with where we were the other day, what we really care about, what you guys really care about, is how is it that I get to solutions, right? How is it that I go through solutions to my problems that we give? And so what I said is I linked you guys to section 6.10 in Zybooks, which is the general process. So I said Zybooks has a bunch of sections in chapter 6. So second order circuits is covered in chapter 6. There's a bunch of different sections there. In fact, in my opinion, way too many sections, because it talks a lot about the differences and very specific equations for a series RLC circuit versus a parallel RLC circuit. In my view, and I think you guys will see this, we can start from a general view and we can look at those things as sort of special cases. Zybooks has too many formulas on this stuff, I think. I like to just keep it pretty basic. All right, you can use those formulas, but we're going to summarize those formulas a little bit here today. So what we said last time is I get these second order circuits, and what I do is I write the differential equation for t greater than or equal to 0. So when I say for t greater than or equal to 0, that means after the switches all sort of move, right, and they've done their thing. The key thing here, I say this guy here is for x of t, right? What did we say that x of t could be last time?
Voltage for
current.
capacitor or current for inductor.
Yeah, so specifically, voltage on a capacitor or the inductor current. So in other words, you're not going to see something for the inductor voltage or the capacitor current. All right. What are these guys related to? V sub c of t and IL of t. What's special about those two things? Anything special you can note about the capacitor voltage and the inductor current as opposed to the other variables we could think about?
It's VC is equal to I dVC d over dt.
Well, so yeah, there's those relationships we have about the current and voltage in a capacitor, in an inductor. But what's special about capacitor voltage, let's say, as opposed to capacitor current?
Do you mean like
That-
how over time it'll
When the,
steady state?
I was-
So not the steady state piece, although it's related to all those things. What's special about current?
when
Go ahead, Eli.
when the capacitor voltage is at its max value, then the inductor current will be 0.
Well, no, and that's not always necessarily true. So I guess maybe the critical piece is these guys are what I call my energy storage variables. Because what's going on in these systems is we're storing energy, right? Or losing it. So what do you mean by, where did I come up with that energy storage variables? Tell me, what's the energy on a capacitor?
Electric field.
Well, it's related to the electric field, right? It comes from it. And what's the expression for that energy on a capacitor?
T V square over
C.
2.
1/2
Oh,
CV squared. All right. And what would it be for an inductor? 1/2 what?
IL square.
Well, Li squared, yeah. Okay. So those are my energy storage variables. We only ever write the differential equations for the energy storage variables. We don't write them for the other variables. We can figure out everything else from these. All right, that's kind of an important thing. So what you'll see in your problems will always be V sub C or I sub L. Okay. All right. So we got 6 steps here. The other day we talked about steps 1 and 2. Today we're going to talk about 3 through 6. Okay. So basically what we said in step 1 is we look at the circuit and we write the differential equation. And so this is a summary page you guys are gonna get when I post these slides. But basically, we're gonna have that form, okay, where A, B, and C are constants of some sort. Now, what did I say last time about A and B? What always has to be true about A and B?
They have to be positive.
Have to be positive.
They have to be positive. Okay, we're going to look here in a second what happens when they're not positive, but it's not good. All right, and it's a situation that nature will not allow. If I have a circuit like you guys have, which is built from things that exist in the real world, it is not possible to have a negative A or a negative B. Those terms can never be negative. Nature does not allow it because it will allow for what we call an explosive situation, where I try to store infinite energy on a capacitor or inductor, and that's just not physically possible. The laws of nature won't allow it, okay? So we'll look at that here in a second, all right? Step 2 is once I got the differential equation, I need to solve it, right? So I basically got to say, that always means that I have a steady state solution, what we called x of infinity, x final, and a transient solution, okay? And then we got to go through the rest of those steps there to go through this. So let me ask you guys this, the second order differential equation, how many exponentials are in that transient response if I have a second order?
Just 2.
2, okay? Now they can be funky exponentials. They can be complex exponentials, which you're learning more about in 2254. If I say it's a complex exponential, what does that mean? What's a complex exponential mean? What am I talking about?
There's a real and imaginary part.
It's real and imaginary part. And those real and imaginary parts with a complex exponential, in 2254, you should be learning that those real and imaginary parts are sinusoidal, right? So it means that I can have this relationship with sine waves. All right, so we're gonna keep going. We're gonna talk about the rest of those steps a little bit later, but I wanted to sort of summarize from last time and then pick up with our example. All right, so basically we get our equation in this form. This equation comes from KCL, KVL circuit analysis, right? We get our total solution in that form, and then I talked about, well, you can guess, you know, in the transient case, you can guess that the transient is an exponential. And if you're not talking, if you guys can mute yourself. All right. So you guess a transient response that's an exponential, and that leads to what we call the characteristic equation. All right. And that characteristic equation comes straight away from looking at the coefficients of this. All right. We could talk more about that, but those are things that you should know from differential equations, and you'll talk more about in 2254, right? What we do to figure out what the transient response looks like is we look at the roots of that equation. So we set it equal to 0, we look at the roots. And if we just do the quadratic formula, we get the roots that are shown here, right? That means I got 2 roots. And what I said last time was we make these substitutions, or I'm going to make these substitutions that Zybooks also makes, to say that alpha, I'm going to make this variable alpha, which is a over 2. So it's basically this a right here. So it's that middle term, right? And then I'm going to make this definition of omega naught. Omega naught is the square root of b. Okay, we're gonna see some terms related to that. So we sometimes this omega naught is called the resonant frequency or the natural frequency. All right, I'm not going to ask you vocabulary questions at any point, but sometimes we give it that name. All right, so what we talked about last time is that what the solution looks like looks very different depending on the relative values of alpha and omega naught, okay? And we talked about this from sort of a very physical perspective, which maybe I'll start there and I'll come back to the specifics there. But I said, essentially, we get to a situation, I can start with a case that we don't usually talk about, which is the undamped case. That's the ideal case, where there are no losses in the system. And we said that so ideally, if there were no losses in my system, the voltages and currents would all be pure sine waves, okay? They'd all be pure sine waves. That's a really useful thing to have in a lot of cases.
What happens in superconductors?
You know, so a superconductor has no losses. That's a device that has no losses.
Okay.
If I wanted to have, so basically, I mean, you're asking a good question. If I had, let's say, this circuit here, okay, and maybe I had a current source right here, okay, that circuit has no losses, ideally. If I just have an inductor and a capacitor, there's no losses in that circuit. This guy can certainly have this as the voltage.
So that would be called an LC circuit then?
That would be an LC circuit, yeah. Now, in reality, there is no such thing as no losses, right? There's wires connecting components, so it's not possible to have no losses. But as you'll learn in later classes, well, I can do some special things with transistors and stuff like that to potentially overcome those losses and make it so that it acts like there's no losses. This particular circuit, for instance, I mentioned the other day, I might call this guy an oscillator. All right, so what is an oscillator? Well, an oscillator is a device that just gives me an oscillation. And your phone uses that, right? Your phone has a 2.4 gigahertz oscillator. that acts as the carrier signal to transmit stuff with Wi-Fi. All right. And so it's a pretty common circuit to have, right? And it looks effectively like this, a current source and an LC. Okay. So that's our ideal scenario. And we said as the losses increase a little bit, you know, we looked at an example of this. As the losses increase a little bit, I still have a sine wave, but what do we call that guy? I guess I have it written here. It's underdamped, right? So in other words, what happens is he is damped. When we add losses, we call that damping. And we see that the amplitude of that guy does what? Well, he decreases, right? And eventually I get to a situation where it just looks like a first order response. I've lost all of that kind of oscillatory nature and gotten to a point where it's just decaying like an exponential. So as our losses increase, I go from basically the ideal situation of oscillation down to just some kind of junky first order system look like response. Okay. So last time what we did was we said, well, how do we know which one is which? Well, what we do is we go through and we look at we go to that characteristic equation, we look at the alpha and omega values, okay? And effectively what we do is from the alpha and omega values, we determine what the form of the solution is. So if, when we said everything comes down to this term right here, this term under the radical, okay? Because what can happen in that, right? So if I look at any term under a radical like that, what's the potential problem I can run into?
Being negative.
Being negative.
Yeah, being negative. And that's actually not a problem. That just means that I get oscillations, okay? So what that means is, so when alpha is less than omega naught, okay, we get the underdamped case, which means that we have this form of the solution right here. If I get into a situation, and that's the case where my roots are complex. Now, if it's critically damped, which I said is really a situation that never happens, that's when alpha and omega are equal to each other. When alpha and omega are equal to each other in the term that I have right here, right? What's true? Well, the radical is going to go away, right? And my roots, what did I call those roots last time? They're going to be both negative alpha, but what are they in this case? I don't know if I said it directly, but they're repeated, right? They're not unique, okay? But they're real. They're real, but they're not unique. They're real and the same. What about the overdamped case? What's true about my roots in this case? Are they real, complex, imaginary? What do I have?
Real one.
They're purely real and they're distinct. There's going to be two different values, okay? There's going to be one for the plus sign here and there's going to be one for the minus sign here, okay? All right. So, you know, it's helpful for us to look at you will probably use these summary pages here. This guy, this guy, this guy, and then that's how we're going to probably go through the approach of trying to solve this, okay? So last time we ended with an example where we were looking at the circuit that's shown on the top right here. So let's actually, I guess I can't delete that while I'm in slide mode, but I want to actually do this slowly here. And I'm going to delete these. I decided I wasn't going to delete them, but I've changed my mind. Yeah. Let's do it again anyway. Stupid things in the way. Okay. All right. So what I want to do is I want to get the differential equation for t greater than or equal to 0. Okay. Now, when we get into that situation, when I'm looking at t greater than or equal to 0, the situation I find myself in is what? What do I have to do with that switch for t greater than or equal to 0? What do I do with that switch?
Go to the 2.
Move it to position 2.
Yeah, it goes to the 2 position, right? So that means that the circuit becomes, here's the 12-volt source. All right. Here's the 60 ohm resistor. Here's the 30 ohm resistor. Okay. And then I have an L and a C. All right, like that. And we were ultimately interested in IL right there. Now, what I said last time is there's nothing wrong with this picture right here, right? I could do this, but I'm going to end up using mesh or nodal or something like that. This is a situation where I typically want to reduce this a circuit. And I drew this dash line and I said, I want to make a Norton equivalent for everything to the left of that dash line that I drew. So if I'm making a Norton equivalent, what does that mean I'm replacing that with?
Current source?
Not just a current source, right? But
And
current
an equivalent resistance
and a
Yeah.
resistance. And where does that resistance go?
in parallel.
Well,
In parallel, yeah. And if you want to know how to do it, it basically works out to be 0.2 amps and 20 ohms. All right, that part, if you're not sure how to do that, go back to the lecture video from last time. All right, that we derived it there. If you're still not sure how to do it, then ask. But all right, here's our simplified system. That, okay? Now what we needed to do is I said, well, from there, let's go ahead and write the differential equation. And notice we've defined again these directions. So I said I sub R is going down, I sub L is going down, I sub C is going down. All right, so what we're gonna do is I'm gonna look at this circuit here. So I'm gonna say I got 0.2 amps and 20 ohms. All right, I'm gonna call that IR. Call this guy here IL, and I call this IC. Okay, and I'm going to call the voltage across the whole thing V sub C. Now, before I started really doing anything with this guy, right, I said there's two relationships that I'm going to need here to really help me. What are the two relationships that I really need to have to be able to do this? What's that?
Initial conditions?
Well, not to write the differential equation. I'm going to need those. I'm going to need those initial conditions. But what are the two other equations I'm going to need? I'm going to need KCl to write a differential equation. But what are the two relationships for the capacitor and the inductor that I'm going to need?
IC
They have the same
equals
voltage.
Well, I think somebody said IC equals what?
CdV CdT.
C dV dt. Okay. And VL is L dIL by dt. Right? I'm going to need those relationships. Now, in this particular circuit, what do I know about VL and VC? What do they have to be?
Yeah, same.
Equal.
They're equal.
Yeah,
They're
they have to be equal, right? So that's a simplification that we were able to make right off the bat. Now, KCL, I'm going to write my KCL. The way I always do it is I say currents in equal currents out. So if I look at this top, if I look at this top node right here, right, I can say 0.2 is the current into that node. And I could say I sub R plus I sub L plus I sub C are the currents going out of that node. All right, now that's going to be the key pathway to getting to my differential equation, but it's not a differential equation just yet. All right, so what's the next step? Well, I got to put in some other variables here. So what I said last time is I'm going to write, well, V sub C over R is going to be that current. IL, I'm going to keep as IL because I want that, right? And then I sub C is C dVC by dt. Now, that is, I guess, sort of a differential equation, but that's not in our standard form, right? Our job right now is to try to get it into the standard form, which looks like this, which means I can only have one variable. And it also means I'm trying to get it into a form where I have a coefficient of 1 on that second order term, and I'm nowhere near that yet. Okay, I'm not too far, but I'm not there yet. So what do I do? How do I, what's my next step to try to get this into maybe just having one variable?
Substitution VC.
Okay, yeah, V sub C. V sub C and V sub L are the same, right? So I can basically plug that in here and I can say, well, the first term becomes L over R DIL by dt. Okay. And the middle term doesn't change. It's still just IL. And the third term becomes what?
D squared VC.
Yep, D squared
I.
IL, D squared IL, right? By DT squared. Times what?
CL.
CL.
Yeah, CL or LC. We, for whatever reason, then we often say it as LC, right? So basically, I'm really close to the form of my differential equation that I wanted, right? The only difference between this differential equation and my standard form is what?
Divide by.
both sides by LC.
Divide both sides by LC, all right? By both sides by LC. So basically, I take this equation right here, and I turn it into 0.2 divided by LC equals D squared IL by dt plus 1 over RC DIL by dt plus IL divided by LC. Okay. All right. Now, at that point, I'm ready to move into my second step, right? I want to figure out now, what I know is that this guy's, his current is going to be IL of t. So it's going to be whatever the final value is plus whatever IL transient looks like. And I want to look at this guy and I want to determine what that transient response is going to be. So basically it gets down to which of these choices am I going to make? Okay. And so we're ready to embark on that journey now and figure out which one of those we're going to choose. Okay. All right. So how do I do that? What should I do? Well, I'm just going to start plugging in numbers, basically. I'm going to start plugging in my L values and all of that. So back to the circuit that we looked at, R was the 20 ohms, right? Because essentially, remember, we were looking at this 0.2 with the 20 ohms in parallel, right? We had this Norton equivalent that we had, like that. All right. And so what I did here, you see my approach, right? Again, here I took a little screen snippet from MATLAB was basically what I did. I plugged in my R value, I plugged in my C value, plugged in my L, and plugged in my I. Okay. And then what I did was I just, sort of said, okay, well, my standard form of the equation was C equals D squared IL by dt squared. And I guess just to be clear, this is a little c. I don't like using c. Little c. Plus a dil by dt plus b times il, like that. Okay. So what I did was, you could see I made the linkage. Here is a. Here is b. And then here is c. Okay. And then what I did was I used those formulas I gave earlier. I said alpha is a over 2, and omega naught is equal to the square root of b. Okay, and I get those numbers here. So in this case, if I plug in those values, I get alpha equals what? Alpha equals 50, and I get omega naught equals 100. So what do I do now? My next step.
Use underdamped.
Use underdamped. And why is that?
Alpha is smaller than omega.
Omega naught's bigger than alpha.
Well, but alpha's smaller than omega naught. Yeah, alpha's smaller than omega naught. So that means that I've got this underdamped response over here. Oh, my mouse pointer disappeared. Yeah, alpha is less than omega naught. And so what that tells me is I've got this response right there, right? That's the equation I'm going to use. I get these decaying oscillations. And that's written in terms of this guy, omega d, all right? So omega d is this guy. That's the limit of the formulas that we need, right? What is written here is the limit of the formulas that we need. So I'm going to go back, and you look, I wrote in here, omega d is that relationship. If I look at my omega d, that came out to 86.6. Okay. Now, because those are omegas, they are frequencies in radians per second. So they do have units of radians per second. All right. And hopefully Yahoo's talking about that. We'll talk more about sine waves actually next week and that notion of radians per second and things like that. All right, but those are our values, and that tells me that I had a response. If I look back at that table, it tells me that that IL of t is IL of infinity, all right, which is our steady state value, plus e to the negative alpha t times d1 cosine omega dt plus d2 sine omega dt, like that. All right. Now, we're not done. If we look at that, we have numbers now for alpha, right? Alpha is equal to 50, we said, and omega d is equal to 86.6. All right. So those guys have numbers. What don't we know here yet? What haven't we figured out?
D1 and D2.
D1 and D2 are unknowns, right? And how do we get those unknowns? What do we need? We need initial conditions. That's right. All right. And what else do I not know technically at this point? We haven't talked about IL of infinity either, right? What the steady state value is. Okay. Now, let's start there. That's actually, if I go back to my process, that's step 3. All right. Step 3 is find the steady state values. And I wrote IL and VC. We can do them both, right? We only need IL, but let's find IL and VC. Okay. So what did we say for that? What did we say that we do when we solve for those sorts of problems? Well, basically, you know, what we saw when we looked at, you know, first order circuits is basically, you know, the idea that always it's the case that if I look at, let's say, a capacitor like this, right? And I have a capacitor in a circuit where it was charged up to some value and then it starts to discharge. What you know happens is that the voltage drops towards 0, right? Eventually becomes 0. And the current, you know, basically there's current that's going to flow in this case. Let me ask you this. If this guy was charged up to whatever VS is, whatever that number is, I don't know, let's just say that's, you know, 10 volts, okay? Why does the current go negative there?
Because the opposite side.
Yeah, because where's the actual charges would have to flow out of this guy in that particular case, right? So it would be moving opposite that sign. So I have a negative current in this case. But what I see eventually is that the current gets to 0, right? Eventually there's no charges moving in that circuit. And there's no charge at all in that circuit because the voltage gets to 0. Now, by comparison, if I look at this particular circuit, where let's say the capacitor voltage started at 0 and rises up to some value. So let's say, again, this is 10 volts, right? All right, so eventually I get to 10 volts. The current still does the same thing and gets to 0, right? What did we say that always means when I get to steady state? If the current in the capacitor always gets to 0, what does that mean about the capacitor?
It becomes an open circuit.
It becomes an open, right? It goes to 0 no matter whether I'm charging it like I am here or whether I'm discharging it like I am here, right? If you look at no matter what, the currents always go to 0. And essentially the relationship says that IC equals C dV dt. So if I get to a constant voltage, the derivative of a constant is 0. So we say this guy has no current, he must become an open, all right? So basically a capacitor becomes an open. That. Now an inductor is the opposite, right? I say VL equals L DIL by dt. And what's going to happen there? I always know that I sub L is going to become a constant. And if I take the derivative of a constant, what do I get? Always.
0.
0. All right. So that says the device has 0 voltage across it and a constant current through it. So there's a current that can move. So I can have a current moving through a wire, but I can't have a voltage across it. So that means I have a short. Okay. So if I look now at, let's say, this circuit, all right, So I could do this, you know, with the current source or without it. So initially, you know, I said I wanted to model it like this. So let's say I had 0.2 and 20 ohms. And we can do this both this way and with the original circuit if you guys want. All right, so once I'm in steady state, what am I going to do with the inductor?
Short it.
Yeah, short it. Okay. Short it. And what am I doing with the capacitor?
Replace it with an open.
Place it with an open. Okay. So I can write this here as IL of infinity, right? And I can write this as VC of infinity. Now, looking at that circuit, what does VC of infinity have to be?
It'd be equal to the voltage across the 20 ohm resistor, wouldn't it?
Voltage across the 20 ohm resistor. So let's start first with what IL of infinity is equal to. What's that?
Wouldn't that be
0.2.
0.2. Right.
It's gonna short the resistor.
Oh.
0.2 amps, right? Because what do I have? If I look around this loop right here, right, I have a 20 ohm in parallel with a 0 ohms. 20 ohms in parallel with 0 ohms is going to be 0 ohms, right? Do the math on that. If I have a short circuit in parallel with a resistance, the short circuit is always going to win, and all the flow is going to go through it. Okay, so so then you ask yourself, well, what's the voltage across that guy? Well, what is the voltage across there?
Be zero.
Be zero. Yeah. So in fact, you could just do KVL around this loop right here, and you would see that you know basically has to be zero. That means there's absolutely no current flowing through that 20 ohm resistor. That's the other way to see that. If I go around this loop right here, right, and I see that the voltage here is zero. If there's 0 volts across a resistor, so if I have 0 equals I times 20 ohms, I has to be 0, right? That's the other way of sort of seeing that, right? There's no way to support a current in something if there's no voltage across it.
Plus, if you consider that everything's connected in parallel, if the voltage across the short is going to be 0, then the voltage across everything has to be 0.
Yeah, once the voltage across, if the voltage across a resistor is 0, there can't possibly be any current through it, right? So a lot of different ways that we could say this. So, okay, now we have that I've got that 0.2 amps. So basically I have that IL of T now is 0.2 plus e to the negative 50t times this d1 cosine 86.6 t plus d2 sine 86.6 t. Okay, so I still have d1 and d2 to figure out. All right, that's where the process gets a little bit different. I don't know, not different, but it's actually quite easy. But we got to think a little bit about the physics here. So analyze the circuit at t equal to 0 minus to find either v sub c of 0 minus or I sub L of 0 minus. Okay, and then set v sub c of 0 plus equal to that. All right, now it's an important concept here. This v sub 0 minus equal to v sub 0 plus and I sub L of 0 minus equal to I sub L of 0 plus. And I say they're important because I got to worry about step 5 here in a second, where I need to analyze the circuit at t equal to 0 plus. So let me just ask before I go too far, when I say 0 minus and 0 plus, what am I referring to? 0 minus.
0 minus is like before you flip the switch, and 0 plus is immediately after you flip the switch.
Okay, I'd say how long before and how long after?
Right before.
Immediately.
Immediately. And it's unfortunately immediately is a relative term because it depends on the way the circuit behaves. But let's say it's probably a nanosecond or a picosecond. Okay, it's a very, very short time right before and after that switch opens and closes. And during that time, those energy storage elements, because of their physics, impose some strange constraints. And those strange constraints lead to the way that we get our steady state conditions. Or sorry, the way we get to our initial conditions. Okay. All right. So looking back here, get back to where we were. All right. So analyzing the circuit, we need to find these guys, right? And so I wanted to try to understand this by looking at, I showed a simulation last time. So what I have here is an LRC series circuit. So I have an R here, I have an L here, and a C here. And you should be able to see there's a plus and a minus across those terminals to define. Here's V sub R, V sub L, and V sub C. Okay. And what I'm measuring here is I have a current meter in series. So this guy, oops, I advanced it. This guy here is I sub L, and this guy here is V sub C. And I said that this voltage source here is 0. So it's basically a short circuit, right? And what I did was before t equal to 0, I set the voltage on the capacitor to 10 volts, and I put the current in the inductor to 0 amps, okay? And for the values I have here, is that guy underdamped or overdamped?
Underdamped?
It's underdamped, right? It's got that sort of decaying oscillation. So I know that this guy is underdamped. Now, if I look at what's going on here, what I see is the capacitor voltage I said, V sub C of 0 minus, is 10 volts. So I see that right there. It looks like right there at time t equal to 0, I see this guy is sitting at 10 volts. And I sub L of 0 minus, I said, was equal to 0 amps. And I see that right there as well, okay? So they're starting out at exactly where I would expect them to be. And I simulated this for, this is 0.7, this is milliseconds. So 0.7 milliseconds is where that time is right there, okay? What I did was I zoomed that in, all right? So if you can see here on the x-axis, these guys, multiply these by 10 to the minus 7 seconds. All right, so that means that right here, 0.1 times 10 to the minus 7 is how many nanoseconds? 0.1 times 10 to the minus 7. Everybody know?
Is that
Nano
10?
is -9, right?
It's 10 nanoseconds.
10 nanoseconds, yeah.
I was thinking.
Yep. Yeah, nano is -9, so that means I got 10 nanoseconds there. So if you look at this, we said that IL of 0 minus, IL of 0 minus was 0 amps, and V sub C of 0 minus was 10 volts. Here, 10 nanoseconds after the switch is moved, what's true about the capacitor voltage 10 nanoseconds after the switch is moved?
It hasn't changed.
Hasn't changed, right? So I'd say V sub C of 0 plus is still the same thing. What about I sub L?
Hadn't changed.
Hasn't changed either, right? And that's important. Basically what I see is that, kind of summarizing this, right? Unless there, and I talked about this a little bit on the very first day, I said, unless there's some way for energy to suddenly leave a system, energy has to always be continuous, okay? I'll explain that idea of leaving the system here in a second, but when I say that energy has to be continuous, that means the energy right before now and the energy right after now, that's what T minus and T plus are. Right before an instant and right after an instant have to be equal to each other. And that's why I say capacitor voltage and inductor current really important. So if energy has to be continuous, what has to be true about V sub C and I sub L? What do they have to be?
They'd be the same as our final voltage, or
Well, no, so it's saying that if energy has to be continuous,
And the voltage and current also have to be continuous.
the voltage and current have to be continuous. Yeah, that's right. So T minus equals T plus. They can't make sudden jumps. In other words, I can't have a discontinuity. That's what that means. They can't be a discontinuity. I can't have the voltage on a capacitor jump all of a sudden, or the inductor current jump all of a sudden. All right, that's not the way nature works. All right. And so as a result of that, I have those statements. And so, what we say is, if we know for a capacitor V sub C of 0 minus, we always know that we get V sub C of 0 plus, like that. And I sub L of 0 minus equals I sub L of 0 plus, right? Basically what that says is, if I look at time t equals 0 minus and find out what the voltage on the capacitor is, find out what the inductor current is, then I can think of, for a really short time, so around t equal to 0, right? Around t equal to 0, for a very short time near t equal to 0, the voltage on the capacitor stays constant. The current in the inductor stays constant. So during that short period of time, what I'm going to suggest then is that I can think of this capacitor as a voltage source, right? I'm going to say it's equal to V0. It could be V0 minus or V0 plus, or just simply V0. Okay. Does that make sense? Right? It's not true. That's not to say the capacitor is always that, but it's basically a constant voltage source for a really short period of time. That guy is a constant voltage source, V sub C of 0, right? What would be the argument that I would make about the inductor? What would I say it is, right? So its current stays constant for a really short time. So how would I model that guy?
Yes, source circle. A source current.
Current source. Yeah, as a current source. So I'll model that guy as I sub L of 0 minus equal I sub L of 0 plus equal I sub L of 0. Right? For a short period of time. In other words, and this is to say, we're going to do an example of this in a minute. That's to say it's a number. It's a constant source. It's not IL of T. It's just a constant current source. Okay? We're going to need that. Right? So the way that we approach this is we basically say, well, we're first going to analyze at T equal to 0 minus, assuming that everything has been in steady state for a while. Okay? And we're going to find out in this step right here, we're going to find out what V sub C of 0 minus is, and we're going to find out what I sub L of 0 minus is. And then at T equal to 0 plus, we're going to replace the capacitors with voltage sources and replace the inductors with current sources, okay? All right, so let's do the first part of that step back to the original kind of example circuit that we've been tracking with, right? So first we got to analyze at T equal to 0 minus, and we always make this assumption that the circuit has been in steady state for a while, right? Meaning all the transients that could have happened, okay? All right, this is just like finding the final conditions. What do I do now? How do I approach this problem?
These are the circles.
So I approach this like I'm looking at a steady state situation. T0 minus is like a steady state situation. T0 plus is something totally different. But at T0 minus, this guy's like a steady state situation. All right, so at T equals 0 minus, what position is the switch at?
Number 1.
Number 1, right? So that means that this guy, I don't even need to worry about that voltage source and resistor, right? I got 0.5 amps. I got 30 ohms. Now, if the circuit has been in steady state for a while, what is the assumption I make about the inductor and the capacitor?
Inductor is a short and capacitor is a open.
Yep, inductor is a short. All right, this guy is a short, so I'm going to call this 0 minus. And the capacitor is an open. All right, this is not particularly different from what we found before. All right, when we were looking at the steady state solution to the total problem. Okay, this is another sort of steady state solution that we use to get an initial condition. Okay, so when I look at this here, this is very similar to what we had before, right? What do we know about IL 0 minus in this case? What's he got to be? What's his number?
0.5.
0.5 for all the same reasons we said before, right? If I've got a short circuit in parallel with a resistor, 0 equals IR times R. IR has to be 0, okay? So all of the 0.5 amps is going through that short circuit. So what's V sub C of 0 minus?
0.
0 volts.
0 volts, okay? All right, so we've got a pretty good handle on what's going on there. Now we got to do sort of that next part, right? I said, all right, then I have to analyze a T equal to 0 plus. So at T equal to 0 plus, what do we know about IL and VC? What have we said about that?
IL is 0.2.
Nope.
It's the same.
It equals the
0.5.
0 plus.
Yep, it's equal.
Yeah, it's equal to the exact flip.
Exact values, yep. And I'm going to turn this into a voltage source, which, you know, is effectively a short circuit, right? Because I have 0 volts. And this guy is basically going to become a current source.
Wait, could you explain again why VC is 0?
Because it's across a short circuit, right? If I do a KVL around this loop right here, V sub C equals 0.
Okay.
And I can do that. I can do a KVL around a loop that has a break like that. So I'm saying basically around that loop, I just have 0 equals V sub C of 0 minus. Like that. It's just going around that rightmost loop. Funky thing about that rightmost loop is it has an open in it. You can write that. That's nothing wrong with that.
So like what if you were like to consider like the entire top portion as like one node? You did like, it was like a node voltage analysis.
So I could do this. So I could go around. So if nodal analysis would be another thing that I could do, right? And nodal analysis would give me the same result, right? I'm just, you know, essentially nodal analysis would say I got 0.5 equals V over 30 plus V over 0, right? I mean, you could go through that process, but it becomes a little bit trickier to see it. I think the simplest way is to say, all right, if I have a short circuit, the voltage across a short circuit is 0 because V equals IR. If I have, you know, 0 resistance, I have to have 0 volts. Okay.
So generally, like if it's in steady state and like it's like a parallel RLC.
Well, I mean, you know, I wouldn't generalize like that necessarily. If it's parallel RLC, yeah, you can. But
if it's next to like,
more important thing is if I have a short circuit, there's 0 voltage across a short circuit.
okay,
Right. That's the thing, the most important thing to really remember.
gotcha.
All right. So basically now that gets me to this step 5. All right, which is I want to analyze the circuit at T equal to 0 plus to find my other initial condition. So I need to, you know, second order differential equations, right? You had an initial condition for the voltage, second order differential equations had 2 initial conditions, right? One for the variable you're solving for and one for its derivative. All right, so I gotta solve for DIL by dt or dVC by dt. Okay, and I say it's 0 plus, and I very explicitly say 0 plus. Let's take a look again at my example circuit here. All right, so if I look at this example circuit and I say, well, let's say I started out with V sub C of 0 is 10 volts and 0 amps. All right, and I have the 0 volt source. The same thing I did before, except I'm adding a measurement here. I added in a voltage across that inductor. All right, so here's V sub L. All right, and I want to see what that's going to look like. So here's what all the results look like. So the inductor current goes down, the capacitor voltage starts at 10 volts, the inductor current starts at 0 amps. But notice the inductor voltage starts at -10. All right, he jumped up all of a sudden. He would have been at 0 before that, and he just jumped up. Because we said initially this guy was a short circuit, so he had 0 volts across it, right? There was 0 volts across that, but all of a sudden he went to -10. Now, I gotta be able to figure out why that is. All right. And if I zoom in, I can definitely see this guy looks like, you know, zoomed in at -10. All right. So what that tells me is that T equals 0 plus, what we already said, right, is I can effectively say that a capacitor at t equals 0 plus, and only at that short time, this guy becomes a voltage source. This guy, the inductor, becomes a current source. In other words, his current is locked in at a particular value. That current cannot change. All right. If the current cannot change, that guy can't be a resistor, right? Because a current and a voltage, or a current through a resistor sets the voltage across the resistor, right? So for that short period of time, we say this guy looks like a current source, this guy looks like a voltage source, and we're going to use that. Okay. So let's think about it in this particular circuit. So this was the circuit I had. I'm going to write it like this. Here's my R. Here's my inductor. And here's my capacitor. Okay. And what I'm going to say is, so we had everything listed like this. Here's V sub R, V sub L, I is going that way, V sub C is going that way. So at t equal to 0 plus, what I said was I make these replacements with a voltage source and a current source. Okay. So I'm going to say that this capacitor is 10 volts. Right? That's V sub C of 0 plus. What do I do with the inductor? What did I say I replaced the inductor with?
Current source.
Current source, right? So I said I made that a current source. Now in this case, that current source is 0 amps. So it's a short circuit, right? But effectively that's a short circuit. It's a current source with or actually I should say it this way. A 0 amp current source is an open circuit, right? No current is flowing right there, okay? So if I looked at that particular loop and I said V sub L is the voltage this way, okay? What is that voltage going to be?
-10.
Negative 10. How did you get that? Well, I showed it, I guess.
Well, KVL says that the voltages around loop are 0, and if there's 10 volts here and there's no voltage across the resistor, then there has to be -10 across the.
And so why is there negative voltage across the, or no voltage across the resistor? Let me ask you that way.
Because it's open circuit.
Because there's an open circuit, so there's no current flowing, right? So across the resistor, I have VR equals 0 times R, right? So I know that has to be 0. Yeah, you're totally right, okay? So now I've got what VL is. If I have what VL is, I know that VL equals L di dt. So now I have that -10 equals L di dt. Now I've gotten the term I need for the second initial condition. Okay, I know what the derivative of the current is at t equal to 0. So I said inductor current and capacitor voltage always have to be continuous. The other variables don't have to be. Okay, and that's where this gets a little bit trickier. All right, it's not hard, but it's just an important thing for us to remember, and we need it to be able to finish solving. All right, so let's assume now that the switch has moved at t equal to 0 plus. Okay, so we said that this particular circuit, we had simplified it down to 0.2 and 20 ohms. Okay, and we had the inductor and we had the capacitor. And you guys had found with me that V sub C of 0 minus was equal to 0, and I sub L of 0 minus was equal to 0.5 amps. All right. So right now at t equal to 0 plus, what do we say were the substitutions we made in the circuit at t equal to 0 plus?
Capacitor is replaced with a voltage source and inductor is replaced with a current source.
Yep. All right. So I have a 0 volt source here, which is the same as a short circuit. And the current source in this case is going to be a 0.5 amp current source. Or yeah, 0.5 amp current source. like that. Okay. All right. The 0.5 amp current source. So if I look at that right there, right, what do I know about this guy here, right? Well, I see that in this particular case, if I wanted to find out what is V sub L of 0 plus, right? That's the voltage across this guy right now. What is that equal to?
0.
0, right? Because I have a short circuit across that current source. That guy is equal to 0, all right? So if I wanted to figure out what's the current in this branch right here, you guys should be able to see that the current in that guy is going to work out to negative 0.3 amps. All right, I'm going to write that there and let you figure that out, right? But that's the current going on in the capacitor. The reason I write this is I say VL of 0 plus is equal to 0 is equal to L di dt. So that tells me that di dt of 0 plus is equal to what? What does that have to be?
0.
Has to be 0. Okay. Now I'm basically done, right? What we had before is with my initial conditions, or which is with my response, I had IL of t was my steady state value. So I'll write it this way: steady state plus e to the negative 50t d1 cosine 86.6 t plus d2 sine 86.6 t, like that, right? Now what I have is that this is, and that IL of infinity, we found this guy was 0.2 amps, right? So now what I do is I say, well, I got two equations that I can write, two equations and two unknowns. IL of 0 is equal to, we found 0.5, all right? And that's equal to 0.2 plus we fill in this guy. So if I put in t equal to 0, what happens to e to the negative 50t?
Turns into 1.
Turns into 1.
Turns into 1. Yeah. What about cosine of 0?
That's still 1.
That's 1. And what about sine of 0?
That's 0.
0. So now I already got, sorry, I need this 0.2 plus D1, right? So now I can see right now that D1 has to be 0.3, right? I've already got one of the terms. Now, my other initial condition comes from DIL by DT, which we found was equal to 0, has to be, well, I have to take the derivative of that top expression, okay? So if I take the derivative of that top expression, what do I get? What's the derivative of 0.2 amps?
0.
0. All right. Now I remember some chain rule stuff here, I guess. I got e to the negative 50t. So I'm going to do it this way. E to the negative 50t times, all right, what's the derivative of d1 cosine 86.6t?
86.6.
Close.
D1.
Negative 86.6.
D1.
D1 sine 86.6t. Right? Plus what?
86.6.
Yeah,
86.
D2. D2 cosine 86.6t. Right? Plus, I got to add in, right, minus 50 e to the negative 50t times the original expression, right? D1 cosine 86.6t plus D2 sine 86.6t. 86.6t, like that. And I need to evaluate this at t equal to 0. And what I'll find is I'll get another equation that'll let me solve for D2. All right. Now that's something straightforward that you guys should know how to do, right? I have 2 equations and 2 unknowns. I mean, we've already figured out one of the unknowns, but that's the last step is to go through that. All right. So I will post videos that have a couple of complete worked examples from start to finish that you guys can look at. And we'll talk more, we'll do some more examples together in class Monday. Okay. And homework 2 will focus pretty heavily on second order circuits. All right. But again, not on exam 1. All right. The exam on Friday is network 1 stuff. Okay. So first order circuits is the last content. All
Thanks
right.
a lot for those videos. That'd be awesome.
Yeah, sure.
Yeah,
No,
appreciate
those are good to have. But one of the things people ask me about, I'm going to try to go in this evening and let me see, I'm going to stop my recording.